Okay, so the previous videos took care of basically all of the rigid motions, the isometries. We had formulas for doing translations, which were very simple. You just add the h and the k if the position vector is hk. And then we did rotations, which had formulas involving sines and cosines. And then we did reflections, which some of those actually had formulas involving sines and cosines and reversing some signs and things like that. Because you had to, in the derivation, we had to rotate the line onto the x-axis and then rotate it back, so we wound up with sines and cosines for that. I'm not going to show explicitly a glide reflection because that's just a composition of two transformations, which would just be a composition of functions using our previous formulas. But the last thing we do need to cover in this section are the similarity transformations, the homotheties, and then of course you can do compositions of those in isometries to do similar figures. Okay, so homothety, or a dilation, is the simpler word for it. Well, a dilation about the origin is actually really easy. If your scale factor is k, if we want to dilate by a factor of k, it turns out all I have to do is multiply everything by k. If we're going about the origin, the new x-coordinate is going to be k times x, the previous x-coordinate. And the new y-coordinate is going to be k times y, the previous y-coordinate. It's a simple little proof. It should be almost obvious that that's the case, but let's look at a proof. So here's the proof they give in the book, but I've constructed it in GeoGebra, and I can change the k value here. So I have the origin and I have the point A, and I've actually used GeoGebra to do the dilation, but here's the point. If k is 1.8, here's this particular picture. I can change that k value to different values, and it doesn't even matter if it's negative or less than 1, the proof is going to be the same. Okay. So basically we've shown before, if you just drop down perpendicular to the axis to get these points B and B prime, which we kind of have to prove that B prime's in that spot, but these two triangles we've proven before are similar. We actually had a theorem that we proved that shows that AB goes to A prime B prime where it's parallel, which means this is a right angle, this is a right angle. They share this angle. By subtraction from 180, they would share this angle, would be the same. So the triangle OAB is similar to OA prime B prime by angle, angle, angle. And the scale factor is k. So by definition of a dilation, OA prime divided by OA is k. Since the triangles are similar, OB divided by OB prime is going to be k. So if we look at these actual coordinates to see that x prime is actually going to be x times k, because x prime is OB prime, which is going to be k times OB. I think I've actually reversed both of these. Yes, it's OA prime over OA is k, OB prime over OB is k. When you cross multiply, OB prime becomes k times OB. I've flipped the reciprocal on both of those. I'm not going to fix it. Just notice that on both of these it should be OA prime. Actually, I will fix it. It's a quick fix. So OA prime divided by OA is k. We stretch to get to OA prime. And then OB prime divided by OB is k. And so if you multiply OB prime, it's just k. So OB prime is k times OB. So x prime is actually, as it should look in the picture, k times x. Now I could do the same thing over on the y-axis to show that y prime is k times y. So it's pretty easy to see, kind of obvious if you look at the picture. If we scale this triangle, if I do OA times k to get A prime, OB times k will give me B prime, and so the x-coordinate is just going to be k times the previous x value, and the y-coordinate is going to be k times the previous y value. A simple composition of functions like we've done before will give us coordinates, and they work out to be pretty easy here, no trig or anything needed. We can get transformations about any point in the plane, and that negative is actually just a typo there. We're doing a homothety, a dilation about the point P by a factor of k. It turns out to be the x-coordinate is going to be k times x minus p, quantity plus p. The y-coordinate is k times y minus q plus q. And that's just because we have to pull p to the origin. Okay. So here's a picture of that. Say I want to dilate about p instead of about the origin by k, and right now I have k equals 2. We'll translate everything toward the origin. So p will go to the origin if we subtract pq, if p has coordinates pq, or hk, or whatever we call them. I'll call them pq this time. A, we're going to subtract off P and Q from that to go to A prime, which is x minus P, y minus Q. Then we're going to dilate by K about the origin, which we saw was easy. We just multiply the new x and y coordinates by K, so we get K times x minus P and K times y minus Q. And then we just translate back. So we add P and Q to get to our new point up here, so if we look at the original picture, we've doubled, K is 2, we've doubled the distance from P. We've scaled from PA out to A triple prime in this case. I kept track of each one with an additional prime. So it winds up, first we have to go toward the origin, so we have the minus P and the minus Q. Then we scale by K. Then we have to shift it back, so we have the plus P and the plus Q there. Okay? So that's it. If you want to do a similarity transformation, it's a composition of these things, and you just do compositions of the functions. I just want to do one application example. You can look in the book for some others, but I'm going to do one. So here we're going to see a proof using transformations and analytic transformations, coordinates for them, to show a pretty obvious result, but still we're going to see how we can use this analytically to do this, to show that the two diagonals of a square are actually congruent to each other. Okay? So I have a square that I've put coordinates on, and similar to some things we did back in section 5.2, it works out easier, instead of calling this side P, to call it 2P. So here's a square where each side is 2P. It goes from 0, 0, 2P, 0, 2P, 2P, 0, 2P. So we know we can find the midpoint using the midpoint formula, and it's clearly just going to be the point P comma P, so M for the midpoint. Now, one way to show these are congruent is to show that it's an image, that one diagonal is the image of another under an isometry, and we now have coordinates to do that isometry. I'm going to show that if I rotate one of the diagonals, and I'm going to take the one that has 0, 0 to make that computation easier, although the other one would be just as easy. We're going to rotate QS about M and show that we get RP, that this diagonal, if we rotate by 90 degrees, lands exactly on the other diagonal, which means they have to have the same length because one was an image of another one under an isometry, which doesn't change distance. And here's the computation of that. It's really straightforward. Like all of these things, it's pretty straightforward just plugging into the formulas. It's a little messy because the formulas are fairly large. So if we start with S, we're going to do the rotation about M by 90 degrees, and we take the point S, which is 2P, 2P. So I go to the formula. We're rotating about the point PP, so it's the x-coordinate of S minus the x-coordinate of P times the cosine of 90, if we rotate by 90, minus the change in the y's times sine of 90 plus P. That's, if you go back and you look at the formula, I've plugged in 2P and 2P for the x and the y, and P for the x and the y from the point we're rotating around. And then the plus h and k on them are also plus p. So there's a lot of p and 2p being plugged into this thing. The cosine of 90 is actually 0, and the sine of 90 is 1. If you work all that out, you wind up just getting 0 and 2p, okay, which is actually r. So if we compute that, we show that s goes from 2p, 2p to the point 0, 2p, which if you look at the picture, if we rotate by 90, s is going to go right on top of r. Okay? And I can show that the other point, the Q, is going to go to the point P. Again, I can just plug that in. Look back. It'd be helpful to have the formula sitting in front of you. But so for the X and the Y in the formula are 0, 0. The H and the K, if we called them that back in the formula, are P and P. You plug all that in, use the fact that the sine of 90 is 1, the cosine of 90 is 0. You wind up with Q being mapped to 2P, 0. Okay? So I can actually physically do that in GeoGebra here if I do the rotation. And that's how GeoGebra works. It uses analytic geometry. So I'm going to rotate, let me do a point at a time, S around M by 90 degrees counterclockwise. And it went right on top of it. It looks a little messy, but S went on top of that. And I won't do any more with it. I'll stop the video there. But that shows me if I rotate QS around M by 90 degrees, I get RP. Okay? So the diagonals are congruent.